Physically, we are talking about uh, velocity field. So it holds in this manner. But mathematically, this RUU can get any value at any tau time displacement or tau lag time. You can think of it as you yourself. You are mostly correlated with yourself, and whoever is close to you in terms on your friendship, your wife or your husband, your friend, your best friend, you are correlated with that guy. So you may not be correlated with someone you don't know. The best correlation you should have, I mean, supposedly, not psychologically, is with yourself. RUU, autocorrelation, is just a mathematical quantification of that. So you may plot this, let's say RUU versus tau, and you will get the most correlation at tau equal to 0. Do I have a plot of this? Yes, I have a plot of this, so I will come to that. If if U1 here, U1 bar, if the ensemble averaged, and RUU, I mean the autocorrelation, are independent of T1. So if they both are independent of the, say, this time that you are starting, then we will call it uh, as weakly stationary process. So weakly stationary process is a process that autocorrelation is only a function of space and the lag, not anymore time. I mean the starting time, and also your ensemble average is only a function of space. So we call this as a weakly stationary process. These are all the definition. It says in ensemble averaging, if I select a time t1 and calculate one average, then if I select another time t1 and calculate another average, they are all the same. The same is true for autocorrelation function. So why do we call it as weakly stationary process? We use this term weakly just to be technically correct, because ensemble average and autocorrelation are not the only statistical functions that we use. There are many other functions that are used to analyze a stationary process. And if all of them, I mean, in addition to ensemble average and autocorrelation, if all of them are independent of T1, then we call it a stationary process. So, or a strongly stationary process. In other words, you have your U and RUU for a weakly stationary, and if all possible joint moments and moments in a process are independent of T1, then it is called a strongly or a strictly stationary process. So the term moment in here that we used um, in statistics is used for statistical parameters that contain only one variable. So you have, for example, first order moment. We call the average of the velocity as a first order moment, or the variance of the velocity as a second order moment. And also we define third and fourth order moments of the velocity by these definitions. So we will come to these later, but uh, we have the definition of moment in here, but parameters like this RUU since you are checking or you are computing u with itself, or maybe with some other variable, these are called joint moments. Okay, so in a strongly stationary process, all joint moments and moments, so both of them, uh, have have to be independent of time t1. Then we call it a strongly or strictly stationary process. So, uh, do you have any question about these moments? Just you have to keep in mind all of these definitions as well. So, what is the first order moment? What is the second order? What is third and what is fourth order moment? And what is variance? What is the standard deviation? I guess you know these definitions before. So just keep all of these in mind. So first of all, if you look at the mathematical definition of autocorrelation, uh, it's a general definition. Okay, this mathematical definition is a general definition. It doesn't care what kind of uh, parameter is included. Just a second. So I said that it doesn't care what kind of parameter is included. So you are using, for example, here u. This could be velocity or some other parameter which may not be even physical. Okay, this is mathematical definition, autocorrelation. So the RUU is a mathematical definition. The fact that what I just described is I have a very inherent assumption that we are talking about a physical system. So we are talking about a velocity field, for example. We have velocity levels which are higher or at least equal to zero everywhere in the field. So everywhere, for example, in the jet. So when you multiply them, the value of this RUU will always be greater than or equal to zero. Second, I told you the highest correlation we observe is at tau equal to zero, right? This is tau, and this is the correlation. This is the variation of correlation versus the time lag for some physical property. And this is only true if we are talking about a physical system like velocity. Mathematically, this RUU can be maximum at any point. So mathematically, it could be maximized at some other tau values. So if U1 is not a velocity signal, just if it is just a random signal, it's not necessary for this point to be highly correlated with itself. Okay? It can have the maximum correlation with some other point or in some other time. But when you are talking about a turbulent flow field, this can never happen. Any point is 100% of time correlated with itself, and the maximum correlation level will be near its neighborhood. Near its neighborhood. This actually has a physical reason. And the physical reason is this: all the fluctuations uh, inside the flow are generated because of the structures, these kind of structures in the flow field. So structures meaning eddies. That's something that I shown in here inside the jet. Again, let me play it for you. So this is a jet, and as you see, uh, these are uh, kind of structures that you're seeing in this animation. Different scale, you're seeing different scales of vortices passing over some point that you are measuring, for example, in here, that you're interested. For example, for a jet flow, the largest size of eddy, the largest size of eddy, meaning that the largest coherent flow structure, uh, it looks like something like this. It may look like a, um, round vortex, for example. It may look like a hairpin type vortex that you're seeing in this animation, hairpin type vortices. And some flow structures are creating these fluctuations. The largest flow structure is generally restricted by the diameter of this jet. So this is the diameter of this jet. And the largest is limited by this. So in a jet flow field, you can never have a vortex which is the size of 10 times of the exit diameter. This means that when these structures are passing over some point, for example, point X or X0, they have a certain size and they are getting convected with a certain velocity. For example, it's being convected from here to here with a certain velocity. So that corresponds to a certain time. Okay, from this point to this point, it corresponds to a certain time. When the same structures are passing through this point, through the point x0, it obviously will generate correlated signals within the domain of the structure, and that would be close to the original point. If you're traveling further and further away, so you are getting to distances, because time separation is also equal to distance separation. You're getting to distances, and those distances are too large compared to the original eddy size. So they will be less correlated. We can say there is a very strong physical reason behind the fact that this autocorrelation function RUU will have a maximum value only at uh, tau equal to zero or near this zero neighborhood. In fact, when you draw this function with respect to tau, I told you for a stationary process, RUU is a function of only uh, x0 and tau, right? So it's not a function of t anymore. So for fixed value of x0, so fixed point in the space, only this point, RUU is only a function of tau. That's how I draw it in this graph. This is why I said we cannot plot. We can plot RUU over tau. When you plot this, generally you will get a distribution like this. So it is kind of for turbulent flow. It's a kind of distribution, and its maximum, as you see, is at tau equal to zero, and it gets reduced when you start traveling away from the point. So since this correlation function shape is related to the size of the eddy, as I just explained, you can just qualitatively determine the structure size that is passing over the point. So which one is bigger when you see the autocorrelation function versus tau? If the structure is small, for example, in this case, if the structure is small, the correlation will die out very quickly, right? So since when it is coming and passing through point x1, since the eddy is small, So the correlation of each point inside the eddy with itself will, in time, will die out very fast, like this orange variation. But if it is a very big eddy, then it will take more time to die, the correlation. So it will take more time for the eddy to pass all the points from point x0. So this blue one, actually corresponds to x0. So what I'm trying to say is this. All these autocorrelation functions are important because we can get a scale information from them. Size. I can plot RUU distribution at many points with respect to tau, and all of them will give me an idea about the size of eddies that are passing through the points, comparing them if there is a strong or weak reduction in correlation. So you can get data at many points. I'm sorry. Did you understand what I meant by correlation physically? Why does it represent the size of eddy?
Yes, I understood, but I will study on more.
Yeah, okay. Okay, what's the unit of this RUU? So I said it's a correlation of velocity with itself, right? Two velocities are multiplied. So it would be meter per seconds, multiplied by meter per seconds. So it has the unit of velocity squared. So this, unit is also the unit of energy, right? So we will see later that autocorrelation function that can be calculated is also related to the energy distribution of turbulence, what we call as energy spectrum of turbulence. The energy, maybe we mentioned it before, this, uh, energy is generated at very high, scales, and it will be transferred to smaller scales. So you're seeing that this energy is being transferred to smaller scales like these, and these goes again to a smaller and smaller ones. And at very, very small scales, this energy gets dissipated. This is dissipation. We discussed, this as energy cascade, and we said that Richardson proposed this cascade. The turbulent flow is composed of lots of eddies of different sizes, right? These are different sizes of eddies and, different energy levels, corresponding to each of them. And when the large eddy breaks up into two, for example, in here, this breaks up into two, energy gets distributed into, these two small eddies. Not evenly distributed. We know that it doesn't go 50% to left one and 50% to the right one. Generally, it goes more, to one of the eddies and less energy to the other one. It goes on and on like this. It goes, like this cascade. When we reach the smallest scales, which we call it as a, Kolmogorov length scale. And, the physical description was made by Richardson in 1920s, but the, uh, Soviet mathematician Kolmogorov developed mathematical tools to represent these energy distribution and using energy spectrum or the power spectra of the autocorrelation function. It is related to the energy in the flow, as we said, uh, the velocity squared. So we will see those details in the coming weeks, and this is just a preview of what is coming. And understanding the scale distribution in turbulent flow is very critical. For example, when people talk about large eddy simulation, we use the word large, and large refers to the size of an eddy. When you talk about large eddy, how do you define this large? With respect to what? So we need a lot of scale information. Also, in addition to ensemble averaging and autocorrelation function, we define simple time average. So you know what is this. So time average of u1 at some specific point is defined by this limit. We use t in here, capital T, for a periodic process, but if it is a random signal, the upper limit of the integral just goes to infinity, the random signal. As large amount of time as possible, you're taking data. I'm only talking about one measurement set. So this is, for example, first measurement. And I have, for example, these 100 samples at each at each second, I get one sample of velocity and I add them up, divide by 100, and so I will obtain time average value. For example, it is equal to this amount. This is just an example. I do it for the second measurement and I obtain another time average value, and I can obtain n number of time average value. The average of all these measurements may not be the same. This could give me n different time averages. But if they are the same, it is a very special case. And this special case is that if time average value is equal to ensemble average, we call this as an ergodic process. So we are talking about an ergodic process. Back to this chart, an ergodic process is also a stationary random process. In terms of our fluid flows, this corresponds to a steady state uh, condition. So ergodic process is a steady state condition. For steady flows, the flow is not changing with time and also with different samplings. So for statistically steady cases, generally we say that du bar dt at a specific point and at specific time is equal to zero, and it is a steady state process. This is the difference regarded to turbulent flows compared to some other random processes. Turbulent flows are statistically random, but the nice thing, especially in terms of engineering, is that they have well-defined statistical properties, well-defined averages, well-defined autocorrelation function, and we will see later even well-defined cross-correlation functions. So cross-correlation means that instead of correlating U with U, we correlate, for example, U with V. So this is called cross-correlation. Also, they have well-defined variances. So statistical quantities are all well-defined. This means that we can design vehicles based on those statistical quantities. We do not need to know velocity at every instant in time. We just need to know the average pressure distribution. We just need to know the average velocity distribution within the wake of a, for example, wind turbine, or within the wake of an airplane, of a wing, things like that. But uh, some processes that occur may not have well-defined statistical properties. For example, the stock market. If you look at a stock market, it looks random and it doesn't look very different than those figures I just showed before to you. But it's not a stationary ergodic process. It doesn't have well-defined average. So some of you may know that when people try to predict a stock market, the simplest approach is what they call as moving average. They locally calculate averages for a few days or for a few minutes, for a few hours, for a few weeks or months, and then they plot these moving averages to catch the general trend of the stock market. So, a stock market, of course, has a physical process behind, which is human being manipulations, but modeling uh, that is another issue. But that signal, although it may look like very similar to turbulent flow signal, the physical processes are different. So it's another story.